We're going to be looking at exponential growth and decay problems, and for the most part, we're going to be looking at how some of the stuff we've been talking about with exponential functions and logarithmic functions applies to real life and different real life situations. We have an exponential decay, could be written like this. Exponential growth would be written like this. If you are dealing with, um, oops, sorry about that. If you are dealing with anything that's non-scientific for growth and decay, you're going to be either dealing with this for non-scientific decay or this for scientific, non-scientific growth. A is your initial amount that you're starting out with. R is your, typically it's a percentage that you got to change into a normal decimal. And T is your time. Often in years, but not always. Now, if you're dealing with more of a scientific situation, then you're going to have y is equal to ae to the negative kt for decay. It's the same thing except your k is positive for our growth. So if it's a scientific situation, more dealing with chemicals and scientific stuff, then you're dealing with the one that has an e in it. If it's non-scientific, you deal with the non-e equations. A, once again, for the scientific, is still what you start out with. T is still your time, often in years, but not necessarily always in years. K is some constant. Sometimes you got to figure that out for your problem. Sometimes you'll be given that. And Y is the amount left over. Now, if you're dealing with this right here, carbon 14, and the half-life of carbon 14, here's your value of K. It may not necessarily be given to you, but if you're ever dealing with the half-life of carbon 14, this is the value of K that you use. If it's not carbon 14, the value of K will be something different. So take a look here. We have coffee, and I'm going to just grab a cup or a sip out of my coffee, so just a second. And I like coffee that has caffeine in it. I don't like decaf coffee. So caffeine is eliminated from the body at a rate about 11% per hour. So how long does it take for 90% of the caffeine to be eliminated from a person's body? I would say this is not exactly scientific, so I would deal with the non-scientific. Since the amount of caffeine is going down, we know it's the decay, so that's why we're doing the one with the minus R. So we are wondering how long for 90% of the caffeine to leave the body, which means 10% of the caffeine's left in the body. So we're starting out with 130 grams, with 10% of it being left in the body. That means we'd have 13 milligrams. Starting out with 130 milligrams, doing 10% because 90%'s gone, only 10% of that's left, it's 13 grams. Y is the amount that you're left with, which in this case is 13 grams. A is what you started out with, which is 130 grams. Then R is your percentage as a decimal. So you got to move your decimal point over 2 spots and get 0.11. And then we're wondering how long, so that means we're looking for our time. So now we have an exponential equation. To solve an exponential equation, you need to get the part with the exponent on it on one side by itself. So you'd have to get rid of that 130. So instead of timesing by 130, you divide both sides by 130. We get 0.1 equals, and by the way, we could simplify what's in the parentheses. 1 minus 0.11 is your 0.89. So now our variables in the exponent, so we're going to want to use logarithms. You could use a natural log on each side. You could use a common log. Either one of these would work nicely. It does not make a difference. I'm going to choose to use a normal common log to the left side and to the right side. You'll notice on the right-hand side, you have your t as your exponent after a logarithm. If you have an exponent after a logarithm, you can always put it down in front. So then you would have t times log of 0.89. So you have t times something, which to get t by itself, all you'd have to do is divide, and you would get this for your calculator ready form. As a side note, if you chose to use a natural log on both sides, you would have gotten t to be the natural log of 0.1 over the natural log of 0.89. Doesn't make a difference. Either one of these would be acceptable calculator-ready forms. Either one, when you type it in, would give you something about 20 hours. We know it's hours because we were told our rate per hour up here. So the only thing that indicated anything dealing with time up here was in hours, so we know our answer would be in hours. Looking at the next problem here, we have the half-life of sodium-22. Well, first of all, sodium-22, I'm thinking that sounds like more of a scientific situation because sodium's an element and sodium-22 is an isotope for that element. We're dealing with a half-life. A half-life is how long does it take for half the material to either disappear or remain. That means we're getting smaller, so it's an exponential decay and it's scientific, so we got to use the one with the little negative sign. Now, we're looking for the value of k, so we don't know what k is, but we know our t is 0.2 or 2.6. The question is, what are we starting out with and what are we ending up with? Well, we're starting out with the whole amount, which is your 1 original amount, and you're ending up with half, so your y is 1/2. So it's not needed to have the 1 in front. So now to get e by itself, I would definitely use a natural logarithm because we're dealing with base e. Could you use a common logarithm? Yes, but a natural logarithm is going to be a lot easier. Take the natural log of the left side, take the natural log of the right side. And remember, natural log on the right side cancels out e. Then to get k totally by itself, all we'd have to do is multiply by the reciprocal of this. That's your calculator-ready form. You type it in. K is a constant. It does not have any units. Looking at this one, we have a woolly mammoth that estimates to only have 3% of the carbon-14. We talked about carbon-14. So that means our value of k is going to be, from what I mentioned earlier, to be this. We want to know, when was the woolly mammoth alive? So I would say, once again, this is more of a scientific. We're dealing with half-life again, so we know it's going to be a decay. So we're wondering how long, so we don't know t. We do know the value of k, so we could put that in. The question is, what are we starting out with? Well, the woolly mammoth started out with, when it was alive, right before it died, 100% of the carbon-14. Well, 100% as a decimal is 1. And it only has 3% now, so we change 3% into a decimal. So now, timesing by that 1 doesn't change it. And then we can go ahead and get t by itself by taking the natural log of both sides. Natural log of the left side, natural log of the right side, and I'm using a natural log because I'm dealing with e. Remember, natural log of your e, they undo each other, so it leaves you just with the exponent. Then to get t by itself, we just have t times something. We just have to do a little bit of dividing. That's your calculator-ready form. We get this. And when you're dealing with half-life of carbon-14, you're dealing with years. So here we have a city of 1 million people. It's growing at a rate of about 3% a year. If it continues at this rate, how long does it take to double? In my mind, I know we're dealing with growth because we're increasing in value. We're not exactly dealing with a scientific situation. There's nothing really challenging about this, so I would say it's non-scientific, and we're growing, so it's in non-scientific growth. So we're starting out with 1 million, so 1 million is what A is. We're looking at it doubling, so that means your output, your Y, would be 2 million. So we have 2 million equaling 1 million. 1 plus r. We know we're growing at 3% per year.
Yep.
So with 3% being my rate as a decimal, I get this. So now I got to go ahead and try to solve this. So I need to get the part with the exponent on it by itself. So I'll divide both sides by a million, add the what's together in the parentheses. So now I can go ahead and easily do the log. I could do natural log or common log, wouldn't make a difference. I'll do a common log to both sides. Exponent after my variable, put my exponent in front. I now have t times something. I go ahead and divide, get my calculator ready form. And so I know it's going to be this. I know my answers in years because I'm dealing with my growth per year.